All right, all right, is this seating chart working for everybody? Is interpretable? And everybody knows what it's supposed to be doing. Any questions about the seating chart? We doing good? Looks good. You know, it was really smart of us to pack people in the seats that where there are fewer, right? You look at the middle section, there's like nothing going on, and then, yeah, so okay. We'll fix that next time, but hopefully everybody's comfortable. You can spread out a little bit too now that you know where you're supposed to be. Obviously the first time we've done this. So our agenda today, does anybody have any questions before we start? Our objective today is to, you remember we're talking about life cycle assessment, and we went really fast at the end of class on Tuesday with respect to this refrigerator problem. So I want to spend about 10 minutes or so on that, okay, just to make sure everybody can do this problem, is comfortable with this problem. Tuesday may seem like a long time ago. We were all tired, up late the night before. Which may still be true today, but you know, some of the terms that we discussed, defining the scope and allocation and system boundaries and all these things. So we need to be clear on the language and then how to do a problem like this. So I got a good sense or a good feeling that the class understood the problem on Tuesday. We didn't go through the calculations. And so, and we're not going to take a lot of time to go through these calculations, but I just want to at least review them with you so you have the chance to ask questions if you have any. Okay, so let me just set the stage on this one. The question that we were dealing with on Tuesday was whether we should buy a new refrigerator or reuse an old one. And, you know, the dirty little secret of life cycle assessment, you can always get the right answer. Or, you know, the answer is always the same. It depends, right? Paper versus plastic, it depends. Modes of transportation. I mean, you can cook up any situation to say whatever you want. And this all boils down to the assumptions that you make. At the end of the day, this is accounting and this is bookkeeping. And it's about keeping the problem clear in your head and making your assumptions transparent. So, you know, when you see these problems, you know, there's a lot of reading to do, right? You saw it with the light bulb case study as well. You know, you have to go through all these pages to figure out what the numbers mean at the end. So for, you know, a comparative life cycle assessment, you know, if somebody just tells you a paper, move on. Like, we all want the short answer, right? We just want to move on. You should be very suspicious. You know, somebody should say, you know, paper if you have 100% recycling and if you don't care about energy and you really just care about air emissions. All right, that would have been the example from the paper versus plastic example last Tuesday. When it comes to a refrigerator, buy a new one or reuse one. It depends on, you know, a lot of things. You know, cost is a factor, but even the assumptions we're making about how the reused refrigerator is being used, when it's being disposed, what are we actually replacing it with. So if you'll remember, the reuse case dealt with a, you know, basically going to the reuse center, picking up an old refrigerator, in this case one that has an electricity consumption of 816 kilowatt hours per year, using it for 10 years and then disposing of it. And then reusing another refrigerator, and it's a refrigerator that happens to be built today. So as if it was the new refrigerator, okay? And that refrigerator is going to have an energy consumption of 248 kilowatt hours per year. Use that for 7 more years and dispose of it. We talk about a functional unit. That was one of the terms we introduced on Tuesday. What is the functional unit of this case study? There's no sentence here that says the functional unit is X. So can somebody figure out what it is? Remember, the functional unit is about an apples-to-apples comparison. Please. Yeah, it's the use of a refrigerator for 17 years in this case. And you know, we could get even more specific than that because, you know, let's suppose that the air conditioner was not being used in an air-conditioned room and it was set really low. It'd be using more electricity, right? So, you know, a real functional unit which you can't derive from this problem statement would be the use of a refrigerator for 17 years to keep its interior at a temperature of, say, you know, 5 degrees Celsius in an ambient condition of, say, 25 degrees Celsius. Because if these two numbers, you know, you see that the reused refrigerator has a high electricity consumption and the new one has a lower electricity consumption, well, you know, were those values determined under the same conditions? The functional unit's what clarifies that for us, okay? So there were some notes on this case study here and, you know, about the cost of electricity. And then this allocation. What did the term allocation mean with respect to this case study? We threw out the fraction 7/17, and we're throwing around this word allocation. What were we talking about? Please. So what we're figuring out is the fraction of those emissions that we're going to attribute to either refrigerator. So, you know, with the new refrigerator, it's really straightforward. We're going to allocate all the production burdens, all the use phase burdens, and all the end-of-life burdens to the new refrigerator. But when you're reusing a refrigerator, there's some real questions. You know, I went to the reuse center, and I brought this refrigerator home. Should the production emissions be allocated to me, right, in terms of the burdens, or should it be to the first buyer, right? And reasonable people can just view it differently, right? What we chose to do in this problem was to allocate of the first, basically you're reusing two refrigerators, right? The first one you're reusing for 10 years, the second one for an additional 7 years. So, you know, and this is completely arbitrary, but it's what we're doing. As we say that none of the burdens from the first refrigerator are going to be allocated to the reuse phase, and we're going to allocate 7/17 of the second refrigerator. So we're using it 7 of the 17 years. Now, when you do these kinds of problems, you may be in a position where you have to make your own allocation assumptions, and that's fine. I mean, you could argue with these. They're completely arbitrary. What you do in the end is what you do a sensitivity analysis. So what if it wasn't 7/17? What if it was 0? What if it was 17/17, right? And you see if the answer changes. Sometimes it does, sometimes it doesn't. We also allocated both end-of-lives to the reuse case. And again, I mean, we can get all hung up on the allocation. In this problem, it doesn't really get changed too much. But I want you to be familiar with allocation as an idea. Okay, does that make sense? Any questions? We'd like you to be able to do this kind of problem. Okay, and you know, you should expect to see it again, and you know, you have some homework to this effect. You know, in this case, you remember there was a strong analogy between life cycle costing and life cycle assessment. And I tried to make the argument, really, we're just sort of changing the units, right? Instead of dollars, now we're talking about environmental attributes. We're still considering, you know, where the product come from, how it's being used, end of life. So the whole life cycle, but we're considering these environmental attributes. And we do allocation in you know, most of what accounting is, the whole practice of accounting is allocation when you start looking at general accounting practice. You have the same issues in life cycle assessment, right? Now, the question here is reusing the refrigerator or purchasing carbon offsets the cost-effective sustainability solution? We can look at life cycle energy consumption as well as cost. We can look at greenhouse gas emissions, okay? Let's start with energy. Okay, we talked about cost last time, and that was pretty straightforward. But what about energy? What is the life cycle energy consumption of the new refrigerator? Just in words, not in numbers. Please. So you have 200 in the case, so you're using numbers, and that's great. For the new refrigerator, we've got 248 kilowatt hours per year. You've got 17 years of use. So that's the use phase. We also need the production phase and the end of life phase. And those were not on this slide, but they were 2 slides later. Oops. Here, so here's the production. So that's 835 kilowatt hours. And then the end of life being 0.13. Okay, so we can just add that up, and we get the life cycle energy consumption for the new refrigerator. We can do the same thing for greenhouse gas emissions. We can do the same thing for sulfur emissions, for NOx emissions. Any questions on the life cycle energy consumption of the new refrigerator? It's pretty straightforward, right? Just addition. What makes the reuse refrigerator harder is that we have this allocation business going on. So I'll just put the problem statement back up. So who can talk us through how we compute the life cycle energy consumption for the reuse case under these allocation assumptions? I'll see if somebody else puts their hand in, then I'll call on you here. That's good. Somebody else? Oh, come on. I'm holding out just to see. Okay, let's break it down. What are the production energy consumption for the reuse case, given the allocation assumptions here? Go ahead. It's 7/17 of one refrigerator because we said that we're going to assume that both of these refrigerators have the same production emissions or energy consumption in this case. So we said the first refrigerator, we're not allocating any of the production burdens to the reuse case. And for the second refrigerator, we're going to have 7/17. Perfect. What's the use phase energy consumption of the reuse refrigerator? How do we do that? Somebody else. Good. The newer one. I like how you call it the junkyard one. That's great. So that's exactly right. Okay, so 10 years of the high electricity consumption and then 7 more years of the lower electricity consumption. We're assuming no degradation. I mean, you can see how we could start to model these things, make it very complicated, but we're trying not to do that here. And how about end of life? Go ahead. Yeah, it's 2 end of life. So, and what we remember from the data was that the end of lives were pretty small, right over here. Okay. So what the skill you need to have here is to understand what the life cycle means. It means production, use, end of life. And then when you have allocation assumptions, to break them down, put them into a table, however you organize yourself, and make sure you're adding up the right numbers. In the end, it's just addition. Okay, you'll get some practice on the assignment 9 doing that. Okay. Now, the fun part is actually getting some answers out. And, I'll just kind of walk you through it. So I also want you to have some skills setting up these problems, like, what should they look like when you put them on your page? How do I make this full screen here? I could zoom, but that's no fun. There we go, full page. Okay, so here, let's start with cost. We did this last time. So you've got the new refrigerator, $800 up front, and you're paying 17 years of electricity cost. So you have to figure out per year what cost of electricity there is. New refrigerator is 248 kilowatt hours per year. It's 10 cents per kilowatt hour. So it turns out the math is pretty easy. It's just $24.80 per year. And that's what you see right here. We can look at the annuity factor for a 17-year payment with a 4% discount rate. The annuity factor is 12.16. So we're going to multiply that $24.80 times 12.16, add it up to the production, or the retail cost of that new refrigerator, and the life cycle cost can be $800. Okay, so we've been doing this over the last couple weeks. The cost of the old refrigerator is more interesting because you didn't pay anything up front, but then you're going to pay electricity for the first 10 years. And then at the very beginning of year 11, or at the end of year 10, you're going to now pay $200 for a reused refrigerator, and it's going to have a different consumption rate for electricity. So you're going to be paying that $24.80 for the last 7 years. So somebody tell me how I'm going to get a net present value given this cash flow diagram. You always do a cash flow diagram. How about somebody from this side of the room? You don't have to do the numbers, just walk me through it. How would I do this? What do I have to take into account? Go ahead. And add them up, exactly. It's exactly how you approach this. So at the beginning of year 11, you have a payment, and then after that, you've got the annuity, just as our friend said. So you got that $24.80 over 7 years. You bring that back to your $11, add it to the $200. Now use your future to present value formula to bring that back to year 0, and then apply the annuity formula, just as was said for the payments in yellow. That's over 10 years. Okay? So that's what you're going to see here. You're going to see that the electricity cost over your first 10 years, now per year, it's $81.60. We already saw for the last 7 years, it's going to be $24.10. Here's the 10 years of payments at 4% with $81.60 per year. That gets you about $662 of electricity payments in the first 10 years. Then we are paying $200 in year 11, but we want to figure out what the payments after year 11 are. So those 7 years of $24 payments per year has a annuity factor of 6. So you see here's 7 years of payments, 4%. The annuity factors turns out to be 6 here. So you're paying $144.60 for electricity from year the end of year 10 to the end of year 17 there. And basically you need to bring the year 11 cost back to year 0. And note that this is the beginning of year 11, so that's actually the end of year 10. So your n in that equation is going to be 10. So this is the future value to present value, and the cash flow diagram, if you read it carefully, it's going to show you're bringing it back over 10 years. So it's the beginning of year 11, not the end of year 11, or the same as the end of year 10. So instead of calling these year 11 dollars, I could call them end of year 10 dollars, because that's the same thing. And that's why this comes back to 10. Okay. So what you get in the end is a life cycle cost for the reused refrigerator of $890 or $95 compared with $801 for a new refrigerator. Okay, so it turns out the life cycle costs of reusing a refrigerator, I mean, what's easier than going and picking up a refrigerator and using it? It seems cheap, right? But it turns out over 17 years it's more expensive. But that's under these assumptions, If the cost of electricity was higher, the new fridge would look better. If the cost of electricity was lower, the reused refrigerator might look better, right? If the upfront costs were different, then the answer might change, right? So the answer always depends on the assumptions. And this is just true for this case under these assumptions. Any questions about the cost aspect of this? I know we've been doing a lot of this. It turns out the cost part's harder than the environmental part. The only hard part about the environmental thing is you have to do the allocation, and we just talked through how to do that. Any questions here? How many people feel comfortable with this type of calculation? You raise them up high? All right, that's a quorum, so we can move on. And these are just the calculations we went over verbally. For the new refrigerator, we look at production energy, use phase energy, end of life energy. So 835 kilowatt hours to produce it, 248 kilowatt hours per year over 17 years plus 0.13 kilowatt hours. And you end up with a life cycle energy consumption of about 5,000 kilowatt hours. Okay? Now, you do not discount environmental variables. Okay? Vineet has been instructed to seek out and kill any question that does that, because discounting doesn't make any sense. It's a financial metric. It's not a environmental metric, okay? So no discounting, which makes it a lot easier. Okay, everybody's got that no discounting of greenhouse gas emissions or sulfur emissions or any environmental impact metric or emissions metric. That makes sense. That will be a federal offense in this class. All right. Now, for the reused refrigerator, remember, as the gentleman up there mentioned, we've got two productions we got to think about, two use phases we got to think about, two end of lives we need to think about. Let's do the allocation. Remember the allocation assumptions, and I've highlighted them in yellow because they're just assumptions. That none of the production burden from refrigerator number 1 is counting. 7/17 of the production of number 2. You've got 10 years in the use phase now at 816 kilowatt hours per year. You got 7 years of 248 kilowatt hours per year. You've got 2 end of lives, which end up being about nothing. And when you add it all up, it's about twice as much energy as the new refrigerator. So not only is the new refrigerator cheaper, it also consumes half as much energy. And I could do this for the greenhouse gas and other air emissions. I'll just hop down to the answer for the new refrigerator over its life has about 3 tons of CO2 emissions over its life cycle, and it's about 6.7 tons of CO2 for the reused refrigerator. So, and that makes sense because most of the energy is consumed in the use phase, and that energy leads to the CO2 emissions. So it makes sense that in a case like this, they would be correlated. But that's not always true. It's only true for energy-using products, energy-intensely using products, like a refrigerator, like a car. For a cell phone, that wouldn't be true. Most of the energy, life cycle energy of a cell phone, just like a plastic bag, is actually in the production. Okay? Questions? How many people feel they could do a problem like this with reasonable confidence? Yeah? All right, that's good. That's good. Are there any questions before we go to the light bulb case study? Yes. When I came up with this, I wanted to just come up with something that you'd say, huh? Like, it doesn't really make sense, right? Why don't I pick some fraction, or why isn't it 0 for both? It's really up to you. And there are more sensible allocations in this one. And I just use this to drive that point home, that's all. It's a good question, yeah. You can get a PhD just looking at allocations of LCAs, and this gentleman up here is actually doing that. So, working on a paper right now. Imagine, think of a glass of Coke, all right? So, sorry, if you don't mind, let's talk about your research a little bit. And you know, the little bubbles in there, right, that carbonated. So where did that CO2 come from? It's a really interesting question, right? Is there like a diesel generator? They're just burning gas to produce CO2, and then that CO2 is going in the Coca-Cola. No, it doesn't work like that. CO2 is an industrial byproduct, right? So fertilizer production or natural gas production, there may be other places you can get CO2 from. But you have this very question, right? To what extent should the drinker of Coca-Cola be allocated the CO2 emissions? Should it be zero? Should it be 100%? Should it be something less than that? Do you use economic metrics? Like, there are a lot of ways you could skin that cat. And, we think that, you should think about this from a market perspective, and we're developing some tools to actually, answer your question, basically. Like, let's bring some sense to this allocation business, right? But when you do a life cycle assessment for real, typically it gets peer reviewed. So there's a lot of groupthink. So when it gets peer reviewed, there's like a group of people who will read it and actually, bless it as a good LCA. So, they'll say, do these allocation assumptions make sense? This probably would not pass muster. But the point is, there's no real right answer. You just got to use your common sense and be able to persuade somebody. Same goes for unit processes, right? Remember, we talked about we have our goal of our study, and then we got to figure out what's inside the analysis and what's not inside the analysis. Right, and I buried that in this problem because the production of this refrigerator was 835 kilowatt hours. But I didn't say what processes were included or excluded, right? And that's got to be part of the LCA too. So you have these same judgment calls showing up all over the place in LCA. We won't do much of that in 265, but if you continue on, take a graduate course in LCA, these issues will come up as well. Any other questions? That was great. Light bulbs. All right, so let me pivot now, and I'll do this quickly. And I want to make sure you understood that, because I didn't hear any feedback from students on this, so I don't know where you're at. So I will find out in a few minutes, I guess. But here's the deal. Okay, and it's kind of the backstory on this case study. So I was looking for LCA case studies that could be easily grasped and could be good, instructional tools, right? So I stumbled across this light bulb LCA. I started reading it, and I'm like, yeah, this is pretty good. Except I found a few places where, this came from the Rocky Mountain Institute, where I think they cooked the books a little bit. And it still passed muster, they still published it, but I think they cooked the books a little bit. For instance, if you read it, you saw that they had this Colorado, this Denver scenario, right? So they look at production in China and then shipment to Denver, right? So Denver kept coming up until they got to the electricity consumption. And suddenly there, they used a national average. And I just said, that doesn't look right to me. And then, of course, if you look it up, which I did, the electricity emissions are actually significantly higher in Denver, right? So, they cook in the books, or are they just being conservative, right? It depends which side of zero you're on. But, these kinds of things come up, and when you see a sudden change, you should start to ask a question. Are they cooking the books, or are they just being extra conservative? If you think that Rocky Mountain Institute is trying to promote environmental sustainability, which they are, then you think they might be cooking the books toward CFLs, these compact fluorescent light bulbs. But they actually chose an emission factor that was about, so the national average, if I remember correctly, and maybe I'm wrong, was about 1,500, what was the unit? So it was, pounds per megawatt hour of CO2 equivalent. So that was a national average. In Denver, it was like 1,900, right? So they actually went to a lower emission factor for CO2 when they switched from Denver to the national average. That actually favors the incandescent bulb that uses more energy, right? So, and if you read it actually carefully, you see a lot of points where they made assumptions that probably bias against the CFL, not toward it. And that, especially if if you're doing one of these studies and you're an environmental group and you happen to get the environmental answer, the first thing you do is you change all the assumptions to be somewhat conservative because people start shooting at you, right? Because this is all about assumptions, right? So I decided to just take this case study one step farther so you could understand sensitivity analysis better. So you look at the Denver scenario. I just made up a Michigan scenario, okay? And those numbers were old. Actually, the light bulbs were a lot more expensive than they are now. So, I went to Amazon.com like any good person, Wikipedia and Amazon.com, right? That's all you need. And here, you look at CFLs, here's 6 of them at 23 watts with a luminance that is roughly equivalent to a 100-watt light bulb, costing $13. That's, almost, well, it's less than half of the light bulb, the CFLs that were in the case study, okay? And I also looked up the 4 incandescent light bulbs were $7 on Amazon. And then I looked up a more current price of electricity. So actually the price of electricity has gone up quite a bit in Michigan since some of my older examples. This was from January, I think. So 15 cents per kilowatt hour, and the offset still costs 2 cents per kilowatt hour. Here's the Michigan number, 1,500 pounds of CO2 per megawatt hour. And then I looked at the emissions, mercury emissions, and these mercury emissions actually were from 2012. These numbers were from 2005. But here's the mercury emission. Okay, and I assume that the CFL lasts 10,000 hours and the incandescent bulb lasts 1,000 hours. And I've had bulbs in my house last longer than this. From grad school, we still got light bulbs. So the ones that we use every day. So that's the situation, and then we asked you to answer these questions. Okay, these 7 questions. Now, who answered the first question before class? I just want to see where everybody is. The group. So group 1. Okay. Second question. Raise them up high. Okay. Question 3. Okay. Question 4. Okay, question 5, 6, and 7. All right, so we're pretty much stacked up like this, okay. Now, here's what I'd like you to do for the next 15 minutes, okay? I'd like you to compare notes on the solution to yours. So if you were group 1, look at your solution to number 1. Talk about how to do it. I'm less concerned about the numbers themselves. I've got numbers. I checked them with Sarang before class, so we think we got some numbers. But this isn't really about the numbers. This is about how to do it, okay? Now, before you start working together, and I meant to remind you to bring a calculator just in case you wanted to do the numbers, but this isn't really about the numbers. I'm throwing a wrinkle at you. So if you answered question 1, I want you to also answer question 3. Now, you haven't thought about question 3. If you did question 2, I want you to answer question 4. If you answered question 3, I want you to also answer question 5. 4 should answer 6 as well, and 5 should answer 1. Oh, wait, how am I doing? Wait a minute. No, yeah, I forgot there's 7 groups, right? So just add 2, all right? So group 6 will do question 1 in addition, and group 7 will do question 2 in addition. Does that make sense? I screw that up. Okay, so 15 minutes, talk about these 2 questions. And Sarang and I are here. If you have questions for us, please ask. All righty. All right. So one thing that will help potentially is to remember what these questions are. What I'd like to do is ask for a volunteer who can just kind of talk us through what needs to happen in each of these questions. And this is important because what I did on assignment 9, you're not wasting your time, because what I did, you know how this compares an incandescent to a CFL? What we're doing in assignment 9 is instead of making the baseline an incandescent bulb, we make the baseline a CFL. Now we look at LEDs. And then you're going to answer these same questions. Okay, so you need to know how to do them. So let me get my solutions. That's not what I was looking for. Okay, all right. Oh, please. Sorry. Oh, there we go. That's the problem. Whoa. All right, sorry, it's just taking me a second here. Okay, so let's see how far you got. Question 1's asking about payback. So the question is, what is the payback time for a CFL under the Michigan scenario? Somebody who answered group 1, just talk us through it conceptually. I've got numbers here. I think they're right. They may not be right. I don't really care about the numbers. I just want you to know how to do it. So how would you compute payback time here? You're really a shy group, huh? Go ahead. That's a nice way to do it. It's a little bit more elegant than how some people might have done it, but it will work. The idea here is to take the cost of a CFL, which is $2.17 on Amazon, and an incandescent, which is $1.75. So you're looking at a 42-cent difference, and you're trying to figure out how long it is going to take you to pay it back. So you have the wattage here. So the functional unit here is a life of a 100-watt bulb. So, but the CFL effectively is only taking 23 watts from the grid. So the delta there is 77 watts. So if your electricity cost is 15 cents per kilowatt hour, and for every hour you use both of these bulbs, the difference is 77 watts. Then really what you look at is I use 77 times 10 to the minus 3 kilowatts times the cost per kilowatt hour, and then you get the cost makeup rate. So you're basically making up 0.1 penny every hour. So how many hours is it going to take you to make up that 42 cents? It's going to take about 358 hours. That's about 90 days. Oh, were you debating over the numbers here? Did you get a number there, or you? I was off by factor of 10. Factor of 10, okay. Missed a zero somewhere or something? Again, it's not the numbers. When we're talking about payback, we're talking about payback of the difference between these two bulbs, right? You could define payback as just, if I spend, relative to a different bulb, right? Like you're going to do in the homework. So you have to always understand what your baseline condition is, and in this case, it's the incandescent. Okay? Any questions about this one? Payback time? Let's go to number 2. What you're going to see is some of these are harder than others. All right, so number 2, the LCA study shows that the CFLs produce 168 kilograms of CO2 equivalent in use over 10,000 hours. How much CO2 equivalent is produced under the Michigan situation? And if Colorado emissions, electricity emissions were considered, how much CO2 equivalent is produced? So I give you the emission factor for Colorado as well. So Michigan was pretty close to the national average, and Colorado was higher, as I mentioned before. So what do you do here? How do I figure out the life cycle energy consumption under the Michigan scenario? Oh, it's not life cycle. It's just asking use phase, right? Yeah, it's just in use. So you don't even need to do the production emissions here. Go ahead.
You take the emission factor in Michigan for the electricity, and you basically just convert it into kilograms per kilowatt hour, and you multiply it by the number of kilowatt hours used by the bulb over its lifetime.
Perfect. And you do the same thing for Colorado as well. So just taking a look at what that looks like here. Sorry, let me. Okay, so doing that, 10,000 hours and converting the emission factor for Michigan into the proper units, kilograms per watt. And you got to bring it over to watts because ultimately that's the wattage of the bulb, it's 23 watts. Okay? And then for Colorado, you do the same thing, but just change the emission factor. So you see the use phase energy in Michigan is about 163.4 kilograms. And from the case study for the national average, I'm just trying to look it up right now. Take me a second. It was 168. So yeah, like I mentioned, so Michigan, a little bit cleaner than the average, but about average. And you see here that compared to 168, the Colorado grid at that time was somewhat dirtier. So I'm using 2005 numbers here. Okay, they're starting to put up a lot of wind out in Colorado, so that number's coming down. Okay, questions on this one? Use phase energy consumption, pretty straightforward. So number 4, this one did generate some questions. So we're looking at shortening the life of a CFL. So, we're talking about a scenario here where these CFLs don't last very long. And the reason I created this scenario is because there's mercury in these bulbs, right? So, let's look at a really aggressively unreasonable lifetime for these bulbs. So the question is, how many milligrams of mercury are released over 10,000 hours of using a CFL bulb if they only last 1,500 hours? And we're using the emission factor for Michigan. So what's the secret sauce to this? How do I do this? Go ahead. Right, so I'm just showing that here to help you out. So the 9.6 was the total from a light bulb. So you need to figure out how much is in production, right? So because you're going to need more CFLs than just one. So you have to figure out how many you need, and it turns out that there's about 0.9, if my numbers are right, milligrams in the assembly phase. Okay, so what do you do after this? So just trying to help you out here. How many did you get? Do you know? 6.67. Okay, and I tried to do the common sense thing, and say that 6.67 is actually 7 because there's no such thing as 2/3 of a bulb. So if you have 10,000, and different people could allocate this different ways, but that's just what I did. So my numbers might be a little bit bigger than yours. Okay, so you have 7 bulbs, and you know how much it takes to produce each in terms of mercury. So what'd you do next? The amount of mercury in the use phase, in other words. Yeah, perfect, perfect. So that's actually what you're seeing evolve here on the screen. So you've got the assembly, 7 bulbs, 0.92 per bulb in the production phase. The use calculation, I have 12.2 down here. And at the end of life, because each bulb has 5 milligrams of mercury, and you got 7 of them, I counted 35 milligrams. So it turns out the use phase is not really the story under this scenario for CFL bulbs. Right. And, you know, you do have to be careful. These bulbs have mercury in them. You know, so now I'll only buy LED bulbs now. I got little kids in the house, and they try to pull on lamp cords, and we got these CFLs all over the place. Keeps me up at night. Not really, because I drink. No, I'm just kidding. See if people awake, or no, I saw some people falling asleep, so I was just trying to see if I don't pass out at night. All right, you're awake. Good. All right. Does everybody understand this? This is the embodied mercury in the bulb, right? So that's why you got to recycle your CFLs. Hey, keep this stuff out of the landfill. And if it breaks, keep your toddlers away from it. Go ahead.
Can we go over how you got the use phase of mercury?
The use phase, I took it, it was in the study. It was in the table.
I mean, the 12.2.
Oh, this one. So this was a Michigan number. So the emissions factor was about 3,000 pounds per 1.2 times 10 to the 8th megawatt hours over 10,000 hours. Then making a conversion to watts, and then basically converting from pounds, which are here, to milligrams here. So there are 2.2, let me see, so a pound, did I mess this one up here? Because a pound, it's 2.2 kilograms per pound, right? Did we check this one wrong or no? For this one? All right, this might be screwed up. So I don't think we actually checked this one. So if you got, go ahead.
I'm wondering why is it different from 3.68?
Because it's in Michigan. This was from Colorado. Or no, actually the use phase, they use the national average, I think, mercury emissions. So this came from the study. So all these numbers came from the study because we needed to figure out from the study what the production emissions were. Okay? Then we're applying this in a Michigan situation. Well, you still got 5 milligrams per bulb in Michigan, and the production emissions of mercury are still the same, but the use phase are different. That's why I have this calculation. Now, whether I got the numbers right, I have to check, and I'll do that before I post it. Okay, but the concept of how to do it's what we're after here. All right, is this making sense? Okay, I actually see some people nodding their heads. That's good. Question 5. Let's just use the information from the case study. And the idea here is let's have the government subsidize each light bulb by $2. And the question is, what's the cost effectiveness of that investment? So you basically figure out how much per 10,000 hours that the government's going to spend, and then divide it by the amount of CO2 saved by going from an incandescent to a CFL. Right. So this, this one is just basically plug and chug. So let me just give this one to you because the next one's a lot harder. So basically they're investing $2 a bulb, and each bulb, and this actually came from calculations previously, you're going to save over the lifetime. So I'm thinking about whether I got this right or not. We did this right. This is on a per bulb basis, right? Not on a lifetime basis. Because this isn't life cycle, right? Because there'd be more than one bulb. Somebody who did number 5, tell us how you did it. Hey, that's good. That's good. Like you say it louder, sorry? You need 10 bulbs. So you're saving, so they're investing $2, right? Oh, that's what I'm missing right now. All right, so the government's only spending $2, but it's actually saving the consumer a lot of money. That doesn't show up in this calculation. So that's why this is only $2. Thank you. You set me straight. So so it's like the government's spending $2 to save you a lot more money than that over the life cycle of these bulbs. Right, but that's not what this question's actually getting at. What this question's getting at is like, okay, well, how much CO2 was saved? So it turns out to be about 730 kilograms minus 168 kilograms. So it's about $3 a ton, which is not a bad deal. You'll remember some of these tables we looked at a couple weeks back on cost effectiveness. And $3 a ton for CO2 abatement, on the market, it might be $5 a ton or something like that. Okay? So, yeah, I got a little bit confused on that one, so thank you. Right, so there's only one investment of $2. I suddenly started thinking there might be more than one investment, but they're getting you to buy the CFL, and it lasts only 10,000 hours, so they're only investing $2. And they're saving 130 kilograms minus 168 kilograms. Okay? I made that look easy. The next problem really is hard. And as I was lamenting to the folks who did question 6, this one's kind of hard. And in the interest of time, I'll just go through it. I did talk with the groups individually who did it. But here's the deal. What this one's saying is, okay, I've got an incandescent bulb. Suppose now I buy carbon offsets for 2 cents a kilowatt hour. Okay? And I've got 10,000 hours. Okay? So I'm thinking about how much carbon is being offset. Okay? So actually, in terms of the use phase carbon emissions, they're all saved, right? And, when I go to offsets, right, it's not like I'm buying fewer bulbs. I'm just buying the same bulbs. And I'm just gladly spending an extra 2 cents per kilowatt hour, okay? And that's going to turn out to be pretty expensive because this incandescent bulb's pretty inefficient, right? Now, if I instead buy a CFL, so I'm comparing now the incandescent to the CFL, the life cycle cost of the CFL is less than the incandescent bulb. So in terms of this question is about cost effectiveness, of course it's going to be more cost effective to buy a CFL because you're getting money back by doing that. It saves you money over the life cycle. Yeah, the purchase cost is higher, but over the life cycle, it's saving you money. Just like a hybrid car. Remember, we gave that example a couple weeks back, right? They actually pay you back. Yeah, they cost more up front, and there's some pain up front, but over the life cycle, you save money. So, of course, it's going to be more cost-effective to buy the CFL than the offsets. However, as several of the groups who did number 6 noted, you're actually going to remove more carbon by buying the offsets, right? Because in the CFL case, you're still emitting carbon in the use phase. And most of the carbon is emitted in the use phase. Okay, and I've got all the numbers sort of laid out here, and we checked them, and I think they're accurate. So I'll just sort of skip to those. But that's the big picture on this, okay? So if we figure out, okay, here's the life cycle cost, first with the CFL, looking at how much carbon they remove over their life cycle. So I think I got about 567 kilogram. Their life cycle cost is $37. For the carbon offset cost, that's $200 just for carbon offsets. And the life cycle cost of the incandescent bulb is about $169. So if I look at cost effectiveness, here for the CFL, I'm buying for $37. I'm saving myself $169, right? And I'm also saving 567 kilograms of CO2. So in the end, that cost effectiveness, it's a negative number, right? It's about $211 per short ton. Like, there's nothing better than free money, right? There's nothing more cost effective than that. For the offsets, I'm spending $200. I am removing 710 kilograms. That's plus $255 per short ton. This is a no-brainer, right? You buy the CFL, right? Or you can do both. You've got the option to do both. And here's the thing about carbon offsets, and it's how we live our life at our house. We buy the carbon offsets, but if you buy offsets, you better be hugely miserly with your electricity consumption. Otherwise, you're just throwing money out the window, right? So if you just buy offsets on inefficient homes, or electricity consumption, like that's like really bad for your pocketbook, right? And if you're a rich person, fine, I'm not. So there we are. We are out of time. I want to have a quiz to reward you for the effort that you've been through. And so pull out, so we won't do question 7. It's one of these subjective ones. Maybe we'll get to it next time. Actually, we might start with question 7 next time. You remember how I told you last time your quiz was going to be list 3 differences between life cycle costing and life cycle assessment? That's your quiz question today. Please just bullet them out and hand them in quietly. Thank you. All right, we are all done here.